For most of human history, the night sky was thought to be a ceiling above Earth, sprinkled with stars, planets, and mysterious lights. To the naked eye, the heavens appeared as a flat, two-dimensional canvas. Even through early telescopes, the universe looked like a collection of stars all belonging to the same cosmic stage. But in the early 20th century, everything changed. Humanity discovered that the universe is not just filled with stars, it is filled with galaxies. Each galaxy is a vast island of hundreds of billions of stars, bound together by gravity, surrounded by invisible halos of dark matter, and scattered across the universe like floating continents in a cosmic ocean. Today we know that galaxies are not just background scenery, they're the fundamental building blocks of the universe. They hold the story of cosmic evolution, the birth of stars, the formation of planets, the emergence of black holes, and perhaps even the origin of life. Galaxies are where the drama of the universe unfolds. Our home galaxy is called the Milky Way. The name comes from the Latin word for milk, and it was given to our galaxy by the Romans because it looks like a streak of milk in the night sky. Through a telescope, the Milky Way resembles a flat pancake, about 100,000 light-years across and 2,000 light-years thick, at Earth located near the center. The galaxy's flat central region is called the disk. It contains a mix of young and old stars, glowing clouds of gas and dust, and a bunch of asteroids and comets. The disk is surrounded by a spherical halo of older stars, followed by a giant sphere of even older stars known as the outer halo. All of these structures are held together by the gravitational pull of the galaxy's central engine, a supermassive black hole. But galaxies come in a wide variety of shapes and sizes. There are giant ellipticals, which are smooth and round like giant cosmic eggs. There are grand design spirals like the Galaxy M51, also known as the Whirlpool Galaxy. And there are many more bizarre shapes like the antennae galaxies, which are being pulled into a giant collision with each other. Galaxies can be as small as a dwarf galaxy in the Canis Major constellation, or as large as the ultra-giant NGC 6093. Our Milky Way is a medium-sized spiral galaxy. It has a relatively calm and stable existence, which makes it an ideal place for astronomers to study the life cycle of galaxies. The first galaxies were born when matter in the early universe collapsed into the first stars. These stars formed into groups, and then those groups came together under the force of gravity to form larger structures. Over time, galaxies grew by assembling smaller galaxies and by accumulating free-floating stars. As galaxies evolved, so did the stars within them. Stars near the center of galaxies tend to be younger and brighter, while stars in the outer regions are older and dimmer. Most galaxies also have a population of ancient stars that orbit around the galactic center, like a swarm of bees around a hive. Some of these stars are so old that they formed in the first few billion years after the Big Bang. Others are so exotic that they cannot be explained by our current understanding of stellar evolution. In the 1920s, the astronomer Edwin Hubble made a shocking discovery that changed our understanding of the universe forever. He found that the universe is expanding. All galaxies are flying away from each other at speeds proportional to their distances. This finding led to the realization that the universe is much vaster than the Milky Way. In fact, the observable universe contains trillions of galaxies, yet despite their vast numbers, all the galaxies in the universe will never collide because they are moving apart from each other. Most galaxies are like islands in a cosmic sea, minding their own business, going about their eternal cycles of birth, life, and death. Some galaxies collide and merge, creating spectacular displays of light and matter. Collisions between galaxies can trigger bursts of star formation and can even reshape entire galaxies. Mergers also bring galaxies together in unexpected ways. For example, the famous antennae galaxies are in the process of merging, and their combined nuclei will eventually form a new supermassive black hole. At the heart of every galaxy lies a supermassive black hole, an object of unimaginable density and gravity. Black holes are so massive that not even light can escape their grasp. They are the engines that drive the evolution of galaxies. They regulate star formation by both destroying and creating stars. They also play a key role in shaping the distribution of matter in galaxies. The existence of black holes was predicted by scientists in the 18th century. but they were not confirmed until the 20th century. Today, astronomers can detect black holes by observing their gravitational effects on nearby matter. Black holes are also one of the most mysterious objects in the universe. We do not know what happens inside them, or what happens to the matter that falls into them. Many galaxies also have dark matter halos. Dark matter is a type of matter that cannot be seen directly. Astronomers can infer its presence by observing its gravitational effects on visible matter. The existence of dark matter was first proposed in the 1930s, but it remains one of the biggest mysteries in modern physics. Galaxies are not just isolated islands. They are connected by a vast network of filaments and sheets known as the cosmic web. The cosmic web is the largest structure in the observable universe. It is also one of the most recent structures to form. The web began to take shape when the first galaxies came together in clusters and superclusters. As the universe expanded, the web grew larger and more complex. Today, the cosmic web is a three-dimensional map of the universe. It reveals the large-scale structure of the cosmos and provides clues to the evolution of the universe as a whole. In this series, we will explore the amazing structures, properties, and evolution of galaxies. We will also explore the latest discoveries about black holes, dark matter, and the cosmic web. Join us as we journey into the world of galaxies. Earth is just a small planet orbiting an average star in an average galaxy. But the story of Earth is also the story of a galaxy evolving over billions of years. We are all children of the Milky Way. We often think of the universe as empty. When we look up at night, we see only a smattering of stars in the vast darkness. But appearances can be deceiving. Between the stars are colossal islands of space-time called galaxies, each home to billions or even trillions of stars. Our own Milky Way is just one among many. If the universe is empty, then why do galaxies exist? Why aren't stars spread evenly throughout space? How do they assemble themselves? And how does the study of galaxies help us understand the origin of everything? Join us as we explore these questions and more, beginning with the most basic. What is a galaxy? At its simplest definition, a galaxy is a gravitationally bound system of stars, gas, dust, and dark matter. But this description hardly captures their true scale. A typical galaxy like our own Milky Way contains over 100 billion stars. The largest galaxies can hold trillions. Surrounding these stars are enormous reservoirs of hydrogen gas, the raw material for future star formation, and vast clouds of dust that scatter and absorb starlight. Yet galaxies are not just collections of visible matter. Observations have revealed that most of their mass is hidden, made of something we cannot see: dark matter. This invisible substance forms an extended halo around each galaxy, keeping its stars and gas from flying apart. Without dark matter, galaxies as we know them could not exist. To put their size into perspective, the Milky Way spans about 100,000 light-years across. That means if you could travel at the speed of light, it would take you 100,000 years just to cross from one side of our galaxy to the other. And yet, compared to the distances between galaxies, even this immense scale feels small. The nearest major galaxy to us, Andromeda, is more than 2.5 million light-years away. The farther we look into space, the more galaxies we see, each like a tiny world filled with stars and planets. As of 2023, astronomers have cataloged more than 100 billion galaxies. But this number is just a small fraction of the true total, because the universe is so vast that many galaxies are simply too far away to detect. And yet, even knowing what we do about the size and number of galaxies, we still don't know how big is the universe. For now, the answer remains unknown. And here's another unanswered question. How did galaxies form? Galaxies are so vast and complex that unraveling their origins has been no easy feat. It was until the mid-20th century that telescopes became powerful enough to resolve the details of other galaxies. Before that, they looked like nothing more than fuzzy patches of light. The breakthrough came with the advent of radio telescopes in the 1950s, which revealed that galaxies were spinning. This discovery, along with observations of their Doppler shifts, provided the first evidence that galaxies were moving through space. Then, in the 1960s, quasars were discovered, extremely luminous objects found at the centers of many galaxies. Their discovery suggested that supermassive black holes played a role in galaxy formation, influencing the behavior of stars and gas within them. With each new discovery, our picture of galaxies grew more nuanced. Today, we are piecing together their history using a variety of techniques. For example, studying the light from distant galaxies allows us to peer back in time to when the universe was young. By observing galaxies at various distances, astronomers can trace how galaxies evolved over billions of years. One such study, published in 2024, used data from the James Webb Space Telescope to analyze the chemical properties of galaxies as far back as 8 billion years ago. The findings suggest that galaxies matured in a way similar to stars, starting small and gradually growing in size and complexity. Another approach involves computer simulations. By modeling the gravitational interactions between dark matter halos, scientists can simulate the process of galaxy formation under various conditions. These simulations help test theoretical models and make predictions that can be verified with observations. One such simulation, called the Illustris Project, simulated the formation of a massive galaxy over 2 billion years. The results were published in 2015 and revealed how galaxies assemble themselves by merging smaller units. Despite these advances, answering the question of how galaxies formed remains a major challenge. Much of their history is imprinted in the oldest stars, but unraveling the chemical signatures in their light is a daunting task. Moreover, simulating the conditions that gave rise to the first galaxies requires enormous computing power. Another big question is, what types of galaxies are there? Galaxies come in a variety of forms and sizes, from the grand spirals to the chaotic irregulars. In the 1920s, astronomer Edwin Hubble created the first classification system, known as the Hubble tuning fork. He divided galaxies into three main categories based on their shape: elliptical galaxies, spiral galaxies, and barred spiral galaxies. Elliptical galaxies are smooth, football-shaped galaxies with little gas and dust. They are dominated by old stars and tend to be quiet, with little new star formation. Spiral galaxies, including our Milky Way, are flat, rotating disks with graceful spiral arms. They are rich in gas and dust and are hotbeds of star formation. The spiral arms are not static features, but dynamic regions where stars are born. Finally, there are irregular galaxies. These galaxies lack the symmetrical shapes of their elliptical or spiral cousins. They are often smaller galaxies that have been distorted by gravitational interactions with other galaxies. Some irregular galaxies, like the Large and Small Magellanic Clouds, are actually dwarf galaxies that orbit larger galaxies. Each type tells a unique story of its formation and evolution. Elliptical galaxies, often the result of galaxy mergers, tend to be found in clusters where their smooth shapes resist the gravitational pull of neighboring galaxies. Spiral galaxies, on the other hand, dominate the outskirts of galaxy clusters, and they frequently engage in star formation, creating beautiful nebulae and stellar nurseries. Meanwhile, irregular galaxies serve as laboratories for studying how gas clouds collapse to form stars under various conditions. A fourth category, known as lenticular galaxies, has recently been proposed. Lenticular galaxies possess a disc-like shape like spiral galaxies, but lack a prominent spiral structure. These galaxies also contain less gas and dust, indicating reduced star formation compared to spiral galaxies. They are often found in the transition zone between rich galaxy clusters and the more isolated regions where spiral galaxies thrive. The study of these different galaxy types helps astronomers piece together the processes that shape galaxies across the universe. Each galaxy is like a book in a library, and by reading the stories encoded in their shapes and compositions, we gain insights into the grand narrative of cosmic evolution. But why should we care about galaxies? Why are they important? Galaxies are not just distant, beautiful objects. They are the building blocks of cosmic evolution. Stars are born within them, live out their lifespans, and end in spectacular explosions. These processes enrich galaxies with heavier elements like carbon, oxygen, and iron, ingredients essential for planets and life. Studying galaxies helps us understand the chemical activity happening across the universe. Galaxies also play a key role in cosmology. Their large numbers are evidence of the universe's remarkable ability to amplify tiny initial variations to enormous scales. By observing the distribution of galaxies, astronomers map the large-scale structure of the universe and probe the nature of dark energy. Galaxies are not just celestial objects. They are the stages on which cosmic drama unfolds. They drive chemical evolution, fuel the life cycle of stars, and reveal the secrets of the universe's structure. Understanding galaxies is not just a matter of scientific curiosity. It is a journey to uncover the roots of complexity in an ever-expanding cosmos. As we continue to explore the vast archipelago of galaxies, each with its unique tale to tell, we are not just discovering distant worlds. We are uncovering the story of our cosmic origins. Galaxies are the chapters in the book of cosmic evolution. By reading their stories, we understand our place in the grand narrative of the universe. Imagine standing on the deck of a ship, gazing out at the endless ocean. You see other ships on the horizon, but you assume they're the same size as yours. As you journey further, you realize some of those distant ships are actually much larger. Suddenly, your perspective shifts dramatically. You realize your own ship is just one among many, each sailing its own course through the vast sea. This revelation is not just a metaphor. It mirrors the journey of humanity's understanding of galaxies, including our own Milky Way. Until the early 20th century, we believed our galaxy was the entire universe. But now we know the universe is filled with trillions of galaxies, each a vast city of stars. So how do we make this extraordinary discovery? How do we determine the size of these gargantuan structures? And what secrets do they hold that could rewrite our understanding of the cosmos? In the early 20th century, the prevailing belief among astronomers was that the Milky Way, with its band of light stretching across the sky, contained all the stars in the universe. Any object appearing as a fuzzy patch of light, known as a nebula, was assumed to lie within our galaxy. However, there was a nagging inconsistency.
Some nebulae
Seemed too large and too bright to be explained as mere clouds of gas and dust within the Milky Way. Among these enigmatic objects was the Andromeda Nebula M31, which looked like a faint, fuzzy cloud in the night sky. It was a source of much speculation and debate. What was its true nature? Was it a featureless cloud of gas and dust, or something more complex? For over 300 years, astronomers grappled with this mystery. Then came Edwin Hubble, an American astronomer who made groundbreaking observations about the nature of the universe. He turned his telescope towards the Andromeda Nebula. Hubble's keen observation and advanced equipment allowed him to measure the distance to the Andromeda Galaxy, proving it was far beyond the confines of the Milky Way. This discovery revolutionized our understanding of the universe. It shattered the prevailing notion that the Milky Way was the sole repository of all stars, opening up the possibility of an infinite number of galaxies beyond our own. Furthermore, Hubble classified galaxies based on their shape, leading to what is now known as the Hubble sequence. This classification system helped astronomers categorize galaxies and study them in a systematic way. Hubble's discoveries laid the foundation for modern cosmology, establishing that the universe is vast and dynamic, a departure from the static view that had dominated scientific thought for centuries. His legacy continues to inspire awe and wonder, reminding us of the boundless curiosity and spirit of exploration that drive scientific progress. However, as the 20th century progressed, it became clear that the universe was even more intricate than Hubble had imagined. Scientists realized that galaxies were not static islands in space, but rather dynamic entities locked in a perpetual dance. The expansion of the universe, the existence of dark matter, and the Big Bang Theory all contributed to a new understanding of the behavior and evolution of galaxies. Despite the evolving nature of our understanding, Hubble's initial insights remain cornerstones in the field of astronomy. His contributions serve as a reminder of the power of observation and the relentless human pursuit of knowledge. Hubble opened the door to a deeper understanding of the cosmos, allowing us to peer into the hearts of distant galaxies and unravel the secrets of the universe. One of the most significant breakthroughs in this endeavor was the advent of the James Webb Space Telescope, which has provided unprecedented views of the cosmos. Launched in December 2021 after years of anticipation and development, the James Webb Space Telescope is a marvel of modern engineering. Positioned about 1.5 million kilometers from Earth at the Lagrange point 2. This infrared telescope is designed to peer deep into space and time, observing phenomena invisible to the naked eye and existing billions of light-years away. Its 6.5-meter gold-plated beryllium mirror and advanced detectors enable it to detect faint infrared signals from distant galaxies, stars, and other celestial bodies.
Unlike its predecessor,
The Hubble Space Telescope, which primarily operates in the visible and ultraviolet spectrum. Webb is optimized for infrared, allowing it to see through clouds of dust, where stars are born, and to observe the faint lights of galaxies that are incredibly distant. This infrared capability enables Webb to look back in time. Because light takes time to travel, the further away an object is, the further back in time we are seeing. Webb can thus observe galaxies and stars as they existed millions of light-years away and billions of years ago, providing a window into the early days of the universe. Webb's mission is not just to look further, but to look back further. It is designed to detect light from the earliest galaxies that formed in the universe, which will shed light on how the universe evolved from a simple hot plasma to the complex web of galaxies and stars we see today. Moreover, Webb will study exoplanets, moons of the outer solar system, and other objects in our cosmic neighborhood. Its sophisticated instruments will analyze the atmospheres of exoplanets, searching for the building blocks of life such as oxygen, methane, and carbon dioxide. By observing these distant worlds, Webb will help scientists better understand the conditions and processes that led to the emergence of life on Earth, and whether similar life could exist elsewhere in the universe. With its unprecedented capabilities, the James Webb Space Telescope promises to revolutionize our understanding of the universe, pushing the boundaries of human knowledge and inspiring future generations of scientists and explorers. As we eagerly await the discoveries that lie ahead, one thing is certain: the Webb will continue to unravel the mysteries of the cosmos, bringing us closer to understanding our place in the grand tapestry of existence. And there are several iconic galaxies that have captured the attention of astronomers and space enthusiasts alike due to their unique characteristics and the insights they provide into the workings of the universe. One such galaxy is Andromeda M31. It's the closest major galaxy to the Milky Way. Andromeda is a prominent feature in the night sky and is visible to the naked eye as a faint, fuzzy patch. It was the first galaxy beyond the Milky Way to be resolved as a collection of stars, and its proximity makes it an ideal target for studying galactic structure and evolution. Another notable galaxy is Messier 87 M87, a giant elliptical galaxy located in the Virgo cluster. M87 is home to a supermassive black hole at its core, which is the focal point of one of the most famous images in astronomy, the first ever image of a black hole's event horizon. This image, captured by the Event Horizon Telescope in 2019, revolutionized our understanding of these enigmatic objects and showcased the incredible capabilities of modern astronomical instruments. The large and small Magellanic Clouds are satellite galaxies of the Milky Way and are visible to the naked eye in the southern hemisphere. These galaxies are relatively small and irregular in shape and are believed to have been disrupted by the gravitational pull of the Milky Way. They are important for understanding galactic evolution and are also home to a variety of interesting astronomical objects, including star-forming regions and supernova remnants. The antenna galaxies are a pair of colliding spiral galaxies that are located in the Canes-Venatici constellation. These galaxies are in the late stages of a galactic merger and provide a unique opportunity to study the effects of collisions between galaxies. The dramatic features of the antennae galaxies make them a popular target for amateur and professional astronomers alike. These iconic galaxies are not just distant objects of scientific interest. They are also portals to other worlds, each with its unique beauty and intrigue. As we continue to explore these galaxies and unlock their secrets, we can expect even more stunning discoveries that will expand our understanding of the universe and our place within it. Now, these distant galaxies are not merely static celestial objects. They are dynamic entities engaged in an intricate cosmic ballet. Their interactions and movements provide valuable insights into the nature of the universe. By observing these celestial interactions, astronomers can gain a deeper understanding of the composition and behavior of galaxies. One fascinating aspect of galaxy studies is the investigation of galaxy clusters. These massive groupings of galaxies are bound together by gravity and provide a unique opportunity to explore the distribution of matter in the universe. By analyzing the motion of galaxies within clusters, Astronomers can infer the presence of dark matter, an elusive substance that makes up a significant portion of the universe's mass. Additionally, studying the collisions between galaxies can reveal valuable information about their structure and evolution. Such collisions can trigger bursts of star formation and reshape galaxies, leaving behind distinctive features that astronomers can analyze to reconstruct past events. Furthermore, examining the distribution of galaxies on the largest scales helps astronomers map the structure of the universe. By observing the patterns and distribution of galaxies, they can identify the filaments and voids that make up the cosmic web, a vast network that stretches across the universe. This web-like structure provides clues about the evolution of the universe and the role of dark energy, mysterious force that is accelerating the expansion of the cosmos. Moreover, astronomers use galaxies as cosmic probes to investigate the properties of intergalactic space. Are on fire in my eye. They can study the distribution and characteristics of intergalactic gas, dust, and other matter. This information is crucial for understanding the evolution of galaxies and the chemical enrichment of the universe. In essence, the study of galaxies encompasses a wide range of phenomena, from the smallest details of star formation to the largest scale structure of the universe. It is a testament to the dynamic and interconnected nature of our cosmos and the ceaseless efforts of astronomers to unravel its complexities. As our understanding of the universe continues to evolve, we can expect even more groundbreaking discoveries and a deeper appreciation for the awe-inspiring wonders that lie beyond our pale blue dot. The sheer scale and complexity of galaxies make them some of the most formidable structures in the universe. They contain hundreds of billions or even trillions of stars, all bound together by the invisible threads of gravity. And yet, despite their immense size and gravitational dominance, galaxies themselves are merely passengers in the grand scheme of things. They ride piggyback on an unseen sea of dark matter, steered by the mysterious force of dark energy. In a way, the history of galaxies mirrors our own journey of discovery. Just as we once explored the continents and oceans of Earth, today we voyage through the uncharted territories of space. Yet, like those early explorers, we often find ourselves at the mercy of what we don't see, unable to chart the full course of what lies beyond our direct vision. Galaxies are among the most studied objects in astronomy. We can describe their shapes, measure their sizes, and count their stars. Yet the processes that govern their birth, evolution, and ultimate fate are still only partly understood. In this segment, we step into the frontier of galactic science where observation meets uncertainty. Theory struggles to keep pace with discovery. 1. The dark matter puzzle, perhaps the greatest mystery of galaxies, lies not in what we see, but in what we cannot see. In the 1970s, astronomer Vera Rubin measured the rotation curves of spiral galaxies, how fast their stars orbit around the center. According to Newtonian physics, stars farther from the galactic center should orbit more slowly, just as outer planets in the solar system move slower than inner ones. But Rubin found something astonishing. The stars at the edges of galaxies move just as fast as those near the center. The galaxies were spinning too quickly to be held together by their visible matter alone. Something unseen, something massive was providing the extra gravity. This invisible mass became known as dark matter. Today, we believe dark matter makes up about 85% of a galaxy's total mass. It forms enormous halos around galaxies, dictating their structure and evolution. Yet despite decades of research, we still do not know what dark matter actually is. Candidates range from exotic particles like WIMPs, weakly interacting massive particles, to ECNs, or perhaps something entirely unknown. Galaxies are, in a sense, shadows of their dark matter scaffolding, Without dark matter, the visible stars, gas, and dust would not form into stable systems. 2. The birth of galaxies, another unsolved mystery. How do galaxies form in the first place? We know that after the Big Bang, matter was distributed almost uniformly, with tiny density fluctuations. Over time, gravity amplified these fluctuations, pulling matter into clumps that eventually formed the first stars and galaxies. But the details are complex. Did galaxies form bottom-up, with small protogalaxies merging into larger ones? Or did they form top-down, with large clouds collapsing directly into massive systems? Observations from the James Webb Space Telescope, JWST, have added new layers to this puzzle. JWST has revealed surprisingly massive and mature galaxies, existing just a few 100 million years after the Big Bang, much earlier than many models predicted. These discoveries are forcing astronomers to rethink how quickly galaxies can form and grow. 3. The role of supermassive black holes. At the center of nearly every galaxy lurks a supermassive black hole, millions or even billions of times the mass of our Sun. The Milky Way's black hole, Sagittarius A**, it's a mass of about 4 million suns. The black hole in M87 is over 1,000 times more massive. What remains mysterious is the relationship between these central black holes and their host galaxies. Observations show a tight correlation between the mass of a galaxy's central black hole and the size of its bulge. The dense central region of stars, somehow, black holes and galaxies seem to co-evolve, influencing each other's growth. But how? Do black holes regulate star formation by blasting out jets and winds that heat surrounding gas? Or do galaxies feed their black holes, which then grow in lockstep? This galaxy-black hole feedback loop is one of the biggest unsolved questions in astrophysics. 4. The missing satellites problem computer. Simulations of the universe predict that large galaxies like the Milky Way should be surrounded by hundreds of smaller satellite galaxies, formed within the halos of dark matter. Yet when we look around our galaxy, we find far fewer satellites than expected. This discrepancy, known as the missing satellites problem, has sparked debate. Are the simulations wrong? Or are the missing satellites real but too faint and diffuse for us to detect? New wide-field surveys are uncovering ultra-faint dwarf galaxies that may help resolve this mystery. But the question remains open. 5. Galaxy morphology and evolution. We can classify galaxies into spirals, ellipticals, and irregulars. But understanding how they evolve from one type to another is still a challenge. Why do some galaxies remain elegant spirals, while others transform into giant ellipticals? What role do collisions and mergers play in shaping galaxies? And why do some galaxies stop forming stars altogether, becoming red and dead? Astronomers suspect that feedback from supernova, active black holes, and environmental effects all play a role. But piecing together this life cycle of galaxies is one of the grand projects of modern astrophysics. 6. Dark energy and the fate of galaxies beyond dark matter. There is an even deeper mystery: dark energy. This enigmatic force drives the accelerated expansion of the universe, pushing galaxies apart faster and faster. If dark energy continues to dominate, galaxies will become increasingly isolated. Over trillions of years, each galaxy or cluster of galaxies will drift into solitude, cut off from all others by the expanding fabric of space. In this sense, galaxies are not just islands, they are islands drifting farther apart in an ever-expanding cosmic ocean. The nature of dark energy is unknown. Is it a property of space itself, a new kind of energy field, or something else entirely? Galaxies, by their distribution and movement, are the best laboratories we have to probe this ultimate cosmic mystery. 7. The human frontier. Despite powerful telescopes and simulations, our knowledge of galaxies is still in its infancy. Every new instrument like the Hubble Space Telescope, the Sloan Digital Sky Survey, or JWST shapes our understanding. We are constantly surprised by galaxies that appear too massive, too luminous, or too ancient to fit neatly into our theories. In many ways, galaxies remain the unfinished puzzle of cosmology. They hold the answers to dark matter, dark energy, and cosmic evolution. But for now, they remain partly hidden, waiting for future generations to unlock their secrets. The universe is big, really big, so big that contemplating it can make us feel worryingly insignificant. And yet our galaxy is where we're from. Its origins, structure, and future are indelibly tied to our existence. Galaxies, in fact, are much more than just beautiful backgrounds to our planet. They are integral to our origins, our daily lives, and our future. Here are 10 ways that galaxies help us survive. 1. The breath of life. At first glance, galaxies may seem remote, vast structures of stars millions of light years away, far removed from our daily lives. It's tempting to think of them as distant curiosities, with little bearing on our existence here on Earth. But in reality, galaxies are profoundly relevant to us. They are the stage on which the ingredients for life were forged, and they continue to shape the environment in which our solar system exists today. 1. The galactic origin of the elements of life, every atom in your body, every carbon atom in your cells, every oxygen atom you breathe, every iron atom in your blood was once forged inside stars within galaxies. Light elements like hydrogen and helium were created in the Big Bang. Heavier elements, from carbon to uranium, were created inside stars and spread across galaxies through supernova explosions and neutron star mergers. Without galaxies as crucibles for star formation, there would be no planets, no chemistry, and no biology. Galaxies are the factories of complexity. Earth, the solar system, and all of us are direct products of galactic evolution. 2. Our home within. We live inside a galaxy, the Milky Way, a barred spiral with about 100 to 400 billion stars. The Milky Way is our home. Understanding its properties helps us understand our place in the universe. The Sun orbits the Milky Way's center at a speed of about 828,000 kilometers per hour, completing one full revolution every 225 to 250 million years. This means the dinosaurs 65 million years ago. Live vet. When the Sun was on a completely different part of its galactic orbit, humanity, and all of recorded history, has taken place in just a tiny fraction of one galactic year. The Milky Way's environment affects Earth in many subtle ways. Stellar neighborhoods, passing near dense star clusters or supernova remnants, could expose Earth to higher radiation levels. Cosmic rays. High-energy particles from supernova in the galaxy constantly bombard Earth, influencing our atmosphere and possibly even climate over geological timescales. Gravitational influences. The Milky Way's gravity keeps the solar system stable within its galactic orbit, while also interacting with nearby galaxies like Andromeda and the Magellanic Clouds. 3. A collision course. Galaxies are not static. They move, collide, and merge. Our own Milky Way is currently on a collision course with the Andromeda Galaxy. In about 4 billion years, the two galaxies will begin to merge, forming a massive elliptical galaxy, sometimes called Milkomata. For Earth, this event will be dramatic to imagine, but not catastrophic to experience. Stars are so far apart that direct collisions between them are extremely rare. Instead, the night sky will transform as Andromeda grows larger, eventually filling the heavens with a dazzling panorama of stars. Over time, the two galaxies will merge into one, reshaping the cosmic neighborhood of our descendants. Any remain to witness it. 4. Galactic hazards. Supermassive black holes at the centers of galaxies can unleash enormous amounts of energy when feeding on surrounding gas. These outbursts, known as active galactic nuclei, AGN, or quasars, can release jets and radiation powerful enough to sterilize entire regions of a galaxy. Fortunately, our Milky Way's black hole, Sagittarius A*, is relatively quiet. But in the past, it may have been more active, sending out bursts of radiation. Indeed, Gamma Fermi bubbles detected above and below the galactic plane suggest that our central black hole once flared dramatically a few million years ago. For life in other galaxies, being too close to an active black hole could mean extinction. Our relative distance from Sagittarius A may be one reason. Earth has remained a safe haven for billions of years. 5. Galaxies as cosmic laboratories. Galaxies also serve as cosmic laboratories where the fundamental laws of physics were tested and confirmed. By studying galaxies, we've unlocked principles that apply everywhere. Relativity. Observing galaxies with high-speed jets and gravitational lensing confirmed. Einstein's theories of space-time. Particle physics, dark matter, revealed through galaxies, has driven some of the most advanced experiments in physics today. Cosmic distance ladder. Measuring galaxy distances gave us the first true scale of the universe. In short, galaxies have shaped our scientific worldview. Without them, we would still imagine the universe as small, Earth-centered, and finite. No. 6. Cosmic address. When we describe our location in the universe, we go beyond Earth and solar system. Our true cosmic address includes our galaxy. Earth gives, solar system gives, Orion arm gives, Milky Way galaxy gives local group, gives Virgo supercluster, gives Laniakea supercluster, gives observable universe. This layered address reminds us that we are not isolated. We are part of a vast galactic system that itself belongs to even larger cosmic structures. The galaxy is not just scenery, it is our home continent in the universe. No. 7. Galactic cannibals. Not all galaxies are passive. Some actively seek out and devour their smaller neighbors. These cannibalistic galaxies grow by stripping their victims of gas and stars, incorporating them into their own stellar populations. Our Milky Way shows evidence of past cannibalism, suggesting we may have grown in this way over billions of years. This violent side of galaxies reveals their raw power, shaping the galactic landscape through consumption and merging. No. 8. Birthplaces of worlds. Galaxies are the cradles of planetary systems. While Earth is our home, it's just one among countless worlds born within galaxies. Each galaxy contains a diverse array of star systems, from those similar to ours to exotic worlds beyond our imagination. Exploring these worlds expands our understanding of planetary diversity and the potential for life elsewhere. Studying extrasolar planets is made possible thanks to the galactic framework that gives us a map of stellar neighbors. No. 9. Sheltering arms. Our solar system resides in one of the Milky Way's spiral arms, the Orion arm. While not the central region, this arm provides unique advantages. It offers a balance between the bustling activity of the galactic core and the tranquility of the outer reaches. This strategic location has shielded Earth from the worst effects of galactic disturbances, contributing to its long-term stability. Number 10. Mysterious signals. The vastness of galaxies extends beyond what we can observe. Astronomers detect mysterious signals coming from deep within the hearts of galaxies. These signals, including fast radio bursts and gravitational waves, offer clues to the behavior of extreme cosmic phenomena. Unraveling these galactic secrets broadens our understanding of the universe and our place within it. By listening to the whispers from within galaxies, we gain insights into the fundamental workings of the cosmos. Galaxies, the grand architects of the cosmos. They spin, they collide, they evolve over billions of years. But until we truly understand them, there are gaps in our knowledge. So today, let's take a ride through the history of how we discovered galaxies. Step 1. The birth of observation. Thousands of years ago, when the Milky Way appeared as a faint, hazy band across the night sky, humans pondered its nature. Was it spilled milk? A celestial river, or perhaps a great serpent? Different cultures saw different things in the Milky Way, but no one understood what it truly was. That all changed in the early 1600s, when Galilei turned his telescope towards the sky for the first time. What he saw was a shock. The hazy band was actually made of countless stars, a collection so vast it was impossible to count them. But while Galileo realized that the universe was much vaster than it appeared to the naked eye, he didn't know the full scale of the Milky Way. We have to keep moving forward if we want to get to the bottom of this. Step 2. William Herschel, In the Shape of the Galaxy. Fast forward to the late 18th century, and we meet William Herschel. With a telescope in hand, he meticulously charted the stars. His goal, to produce the first map of the Milky Way. After counting thousands of stars, Herschel concluded that the Milky Way is a giant flattened disk. And where did he believe the sun to be in this disk? Right in the center. Now we know that's not quite right. The sun isn't in the center, but Herschel's contribution was monumental. He had taken the first steps in charting the structure of the galaxy. Step 3. The nebulae catalogs. Around the same time as William Herschel was busy mapping, other astronomers like Charles Messier were busy listing. They were creating catalogs of space fuzziness, patches of light known as nebulae. Some of these turned out to be star clusters and gas clouds within our Milky Way. Others, however, were spiral-shaped and didn't fit into the standard explanations. These included the famous Andromeda Nebula. At the time, scientists were split. Were these spiral nebulae just strange clouds within our galaxy, or something more profound? Could they be entire galaxies of their own, separate island universes? We'll come back to the big debate soon. But for now, let's keep exploring. Step 4. The Great Debate of 1920. As the 1900s dawned, two camps had formed. One argued that spiral nebulae were part of the Milky Way. The other believed they were separate galaxies. The main supporters of the first view were led by Harlow Shapley, who argued that everything we see is part of the Milky Way. Everything. On the other side was Heber Curtis, whose team believed that some nebulae were in fact separate galaxies. The debate was fierce. No one could prove their case conclusively. And then Edwin Hubble stepped in. Step 5. Edwin Hubble and the Expanding Universe. Edwin Hubble, armed with one of the most powerful telescopes of its day, the 100-inch Hooker telescope at Mount Wilson Observatory. He set out to study the Andromeda Nebula. His target, Cepheid variable stars, stars that change in brightness and period. These stars are supernovas that have slowed down to a steady glow. They are the galaxy's most reliable rulers, allowing us to measure cosmic distances. Hubble counted the periods of these stars in Andromeda and measured their brightness. With these two values, he could calculate their distance, and his conclusion was a bombshell. Andromeda was much, much farther away than anyone had imagined. This discovery shattered the prevailing idea that the Milky Way was the entire universe. The universe was bigger. There were other galaxies. The implication was huge. What Edwin Hubble had done was show that the universe was full of galaxies, each possibly containing billions of stars. It was as if someone had walked up to you and said, "You think the Earth is big? Wait till you see the moon." And then when they turned around, you see the entire solar system. But Hubble didn't stop there. He took redshifts and starlight seriously. He noticed that the light from distant galaxies was stretched, shifted towards the red end of the spectrum. He interpreted this as galaxies receding from us. In 1929, he published the evidence that the universe itself was expanding. So not only had he shown that the Milky Way was just one galaxy in a vast universe, he had also demonstrated that the universe was growing. What a revelation. Step 6. Vera Rubin and the dark matter revolution. It's just like Hubble. Vera Rubin wanted to understand how galaxies worked. 8. She focused on a galaxy's rotation curves, how fast stars revolve around the galactic center. If a galaxy is like a planet orbiting a star, you would expect the outer stars to go around the center slower than the inner ones, right? You know how the planets in our solar system orbit the sun? The farther they are from the sun, the slower they move. Well, that's exactly what Rubin expected to see. But her observations told a different story. Stars far from the galactic center were moving just as fast as those closer in. What was going on? How could all those stars be moving so fast without flying apart into space? Rubin figured that there must be something invisible holding the galaxies together, something that we can't see but that has gravity. This invisible stuff became known as dark matter. Rubin's work was a revolution because she showed that galaxies are just made of what we can see. They're surrounded by a lot of invisible stuff too. Step 7. The Hubble Space Telescope, a window on galaxies. Let's jump ahead to 1990 when the Hubble Space Telescope was launched into space. It was a revolutionary moment. Why? Because above the Earth's atmosphere, Hubble could capture incredibly sharp images of galaxies throughout the universe. It peered deep into space and snapped photos of thousands of galaxies in tiny patches of sky. And here's the amazing thing. Those galaxies were so distant that they were as they existed billions of years ago. Hubble essentially gave us a time machine. Not only did it reveal that galaxies fill every corner of the cosmos, but it also allowed us to see them as they were in the past. It was as if Hubble opened a window to the history of galaxies, letting us look back in time. Step 8. Mapping the universe. The Sloan Digital Sky Survey. In the early 2000s, a major project was launched to map the sky. It was called the Sloan Digital Sky Survey. Using a special telescope, SDSS systematically photographed millions of galaxies. Its goal was to understand how galaxies are distributed throughout the universe. And what it found was nothing short of incredible. It revealed a vast cosmic web. Galaxies were arranged in enormous clusters and sheets, separated by vast, empty spaces.
Ow!
This web-like structure is not just an image. It tells us about how matter is distributed in the universe. It's like the scaffolding on which cosmic structures are built. The discovery completely changed our view of galaxies. It showed that galaxies don't exist in isolation. They are interconnected in a grand cosmic dance. Step 9. The James Webb Space Telescope and beyond. Well, here we are in 2023 with the James Webb Space Telescope in operation. And the discoveries it's making are rewriting the history of galaxies. With its infrared vision, Webb can look back further in time than Hubble. Right? And what it's showing us is astonishing. Galaxies as they formed just a few 100 million years after the Big Bang. And here's the twist. These early galaxies seem larger and more developed than expected. It's as if you were expecting to see baby pictures of your friend, and you see him already looking like a grown-up. Astronomers are scratching their heads trying to figure this out. The early galaxies challenge existing models of how galaxies evolved. The universe of today seems to be giving us clues about itself. The James Webb Space Telescope is just the latest in a long line of instruments that are advancing our understanding of galaxies. Soon, the Vera C. Rubin Observatory will start surveying the skies. The Nancy Grace Roman Space Telescope will hunt for exoplanets, and the Square Kilometer Array will listen to the radio waves from pulsars.
Yes.
Each of these projects will bring new discoveries, deepening our mysteries. Step 10. The scientific journey continues. The study of galaxies is a testament to human curiosity, ingenuity, and our relentless pursuit of knowledge. From Galileo's first glimpses to Rubin's dark matter revelations and Hubble's breathtaking views, each step has deepened our understanding of the cosmos. But the journey doesn't end here. With new telescopes and theories, we are poised to unlock even more secrets of galaxies. Who knows what wonders await us in the vast expanse of the universe? Perhaps we'll find answers to our deepest questions, or maybe we'll find ourselves lost in a labyrinth of even greater mysteries. But one thing is certain, the journey of discovery is never ending. As long as we keep asking questions and searching for answers, the universe will continue to reveal its secrets to us. And who knows? Maybe one day we'll even map the very edge of the universe and discover that we're reliving in a galaxy of trillions, not billions. I'm here with Earth. Galaxies are big, like really, really big. Our home galaxy, the Milky Way, contains more than 100 billion stars and stretches, more than 100,000 light-years across. And our solar system is just one of trillions of systems contained within this giant cloud of dust and plasma. But galaxies aren't just big, they're also numerous, like really, really numerous. There are at least 100 billion galaxies in the observable universe, each packed with trillions of stars. And together, these galaxies are grouped into clusters and superclusters in a vast cosmic web. The sheer scale of the galaxy-studded universe can be hard to wrap your mind around, but that hasn't stopped humans from trying. Now, armed with some powerful telescopes, we've managed to peer deep into space and time to assemble a pretty good picture of our place in the grand scheme of things. And we've learned that galaxies can tell us not just what they are and how they formed, but also what our cosmic story might say about where we came from, where we're headed, and whether we're alone in the universe. But first, let's make sure we have a common understanding of what a galaxy is. Galaxies are enormous collections of stars held together by gravity. Stars in a galaxy rotate and orbit around a common center, and they regroup together in a flat pancake-shaped structure called a disk. The Milky Way is a spiral galaxy, with spiral arms extending out from the center. But different galaxies come in all shapes and sizes, from small spherical ones called dwarf galaxies to the giant and oddly shaped ones called irregular galaxies. Some galaxies are barred spiral galaxies, which have a bar-shaped grouping of stars in their center. Others are lenticular galaxies, which have a disc-like spiral galaxies, but without the prominent arms. And still others are elliptical galaxies, which have an oval shape and a smooth, featureless appearance. The largest galaxies contain trillions of stars and stretch tens of thousands of light years across. And the smallest galaxies contain only a few hundred stars and measure just a few dozen light years across. You might think that all those different shapes mean that galaxies must have formed in different ways, and that's right. Galaxies don't form fully formed. They grow over time as gas and dust clump together under the influence of gravity, gradually building up a collection of stars. When these clumps start to get big enough, gravity pulls them into a roughly spherical shape. And if they keep gathering material, they eventually become massive enough to pull themselves into a disk shape. A rotating disk is more stable than a random clump of matter. And a rotating disk with a bit of a bulge in the middle is even more stable than a perfectly flat one. So in the end, you get spiral galaxies like the Milky Way. And while most galaxies seem to follow this basic recipe, the details vary, and scientists are still working to understand why. Consider the fact that some galaxies are huge and some are small, or that some galaxies have disks and others don't. Astronomers are beginning to learn that these differences depend on things like the strength of gravity and the amount and distribution of dark matter, an invisible substance that makes up a quarter of the mass in the universe. Because galaxies can come in so many shapes and sizes, they're actually really complicated objects. And scientists study them from lots of angles, which requires a lot of telescopes. For example, the James Webb Space Telescope, which launched in December of 2021, was designed to peer deep into space to detect light from the earliest galaxies, as well as to take infrared pictures of things, like exoplanets and other systems that exist outside of our Milky Way. Meanwhile, the Square Kilometre Array, currently under construction in South Africa and Australia, will link up 197 radio dishes and 86 small satellite dishes in what's basically the world's biggest radio telescope. Its purpose is to measure the properties of pulsars, neutron stars that emit beams of electromagnetic radiation as they spin. Some of these radio telescopes will focus on fast radio bursts, quick pulses of radiation that last only a few milliseconds and seem to come from far beyond the Milky Way. Astronomers are still working to figure out what causes these bursts, but they think it could be everything from a magnetar, a type of neutron star with an extremely powerful magnetic field, to a flare from a supermassive black hole. Okay, so now we've got all these tools to measure and analyze galaxies. But what exactly are we hoping to find? Well, it turns out that galaxies can tell us all kinds of stuff about the universe and our place in it. First, they can help us better understand our home turf. Right now, the Milky Way is slowly moving toward the Andromeda Galaxy. In about 4 billion years, the two will collide in a cosmic dance of gravitational tides and stellar reshuffling. Though the word collision sounds catastrophic, the vast emptiness of space between stars means Earth is unlikely to strike another star. Instead, the merger will reshape both galaxies into a massive elliptical system. Over billions of years, this new galaxy, sometimes nicknamed Milkomata, will settle into a calmer state, with fewer new stars forming. Our descendants, if they survive that long, may look up and see a night sky filled not with the familiar Milky Way, but with the stretched and merging form of Andromeda overhead. In addition to predicting the future of our galaxy, the study of galaxies helps us peer into the distant past because galaxies are so far away. When we see them, we're seeing them as they were in the distant past. By studying the characteristics of galaxies that existed billions of years ago, astronomers can work out the conditions that led to the universe that we inhabit today. Galaxies are also key to figuring out the fate of the universe. That's because galaxies are engines of star formation. Stars are born from clouds of hydrogen gas, and over time, galaxies use up this fuel. Already, many large elliptical galaxies are red and dead, forming no new stars. In trillions of years, galaxies across the universe will exhaust their gas supplies. Star formation will cease, and the universe will grow darker as old stars burn out. Galaxies, once vibrant with stellar nurseries, will fade into quiet islands of long-lived dwarf stars, and that raises another important point. The study of galaxies also tells us something about the growth and evolution of stars. Stars come in a range of sizes and colors, and their size and color are closely related to their mass. Massive stars are blue or sometimes yellow, while less massive stars are red. And as stars go through their life cycle, they change color as well. When a star is born, it begins with a burst of hydrogen fusion in its core, which gives it a bright, hot glow. As the star ages, it fuses heavier and heavier elements, and its core shrinks and heats up. Eventually, the star becomes so dense that electrons are forced to combine with protons in its core, producing mostly iron. At this point, nuclear fusion stops, and the star collapses under the force of its own gravity. Depending on its mass, it may end its life as a white dwarf, a neutron star, or a black hole. Studying how stars die can help us understand what elements are necessary for life as we know it. Since many of the elements essential to life, including carbon, oxygen, and nitrogen, are forged in the cores of massive stars that end their lives in spectacular supernova explosions. Galaxies also help us study the evolution of black holes, regions of spacetime with gravity so strong that not even light can escape their grasp. Black holes have a radius called the event horizon, which marks the point of no return for anything that strays too close. And right at the center of most galaxies, including the Milky Way, lies a supermassive black hole. Watching how galaxies move and evolve helps astronomers track how supermassive black holes grow and influence their host galaxies. One prevailing theory suggests that supermassive black holes formed early in the universe and grew by consuming gas and merging with other black holes. The evidence for this comes in part from the motion of stars near the center of galaxies. Stars in the immediate vicinity of a supermassive black hole move incredibly fast, and they can even orbit the black hole multiple times per year. By measuring the speeds of these stars, astronomers can calculate the size of the central black hole. And finally, the sheer number of galaxies raises questions that stretch beyond physics. If there are 2 trillion galaxies, each with hundreds of billions of stars, then there are likely trillions of habitable worlds. Is Earth unique? Or are there countless civilizations scattered across the cosmic archipelago? Do galaxies serve as cradles of life, or are most silent? And if intelligent life exists elsewhere, how do they perceive their own galaxy? Galaxies are not just scientific objects, they are the possible homes of unknown cultures. Minds and histories, separated from us by impossible distances. So galaxies are pretty awesome, and we're lucky to be living in an era when we can observe them in such exquisite detail. But in the end, they are just one part of our cosmic story. To truly understand our place in the universe, we need to keep asking questions and keep looking up.
Thanks for watching this episode of Show Space, which was brought to you with the help of our patrons. If you'd like to help us make more videos like this, you can get started at our support page.